To that, though, I was down by Lake Michigan the other day, and if you've ever been down there at springtime, the water is exceptionally cold, and there's a fair amount of crabs down there. Can anybody tell me why it is that you should never, ever, under any conditions, trust a crab?
Cancer.
Well, I mean, that is a constellation with the crabs in it, yeah.
They're snappy.
They're snappy.
They give you crabs.
Oh.
Okay.
Okay.
Yes, it is. You should never trust a crab because they're just so shellfish.
Oh my God.
That was bad.
That doesn't make sense though, because they're not fish.
That was bad.
They got shells.
They're crustaceans.
Thermodynamics is what we're going to be talking about today, and by the end of this you'll have at least a basic understanding of how it is that these steam trains that you see in old westerns actually work. We're going to talk about heat, we're going to talk about all sorts of things, and so sit back and enjoy your adventure into the world of thermodynamics. Being thermodynamics, basically what it means is it is the study of heat, how heat works, because thermo means heat. Dynamics mean how it works. So how heat works. So this is just a little temperature scale thing. You can see we really have three different scales here. We've got Fahrenheit that we're all used to. We've got Celsius and we've got Kelvin. They're all kind of different. Fahrenheit's really good for everyday measurements because you have a nice big span, from 50 degrees to 80 degrees that people are comfortable in. Celsius has some other advantages. 100 is the boiling point of water. 0, of course, is the freezing point. And Kelvin has its own special things. Kelvin goes all the way down to 0 Kelvin, and that is the coldest anything can ever possibly get.
So
Things
from the bottom.
Yes. So things get cold and hot based on molecular friction. And that's what gives you heat, and that's what gives you coldness. And, in the same way that you get warm by rubbing your hands together, molecules are doing the same thing when the air is warm. And once you reach 0 Kelvin, basically you have absolutely no molecular movement whatsoever. So if those molecules aren't moving, they're not producing any friction between them, and there's no heat being produced. So at that point, you can't get any colder, and that's what 0 Kelvin represents there. Now, let's say I've got two pieces of paper, and I blow between them. Any guesses on what is going to happen to these two pieces of paper? They're going to go outwards. Anybody else? Michael says they're going to go inwards.
What?
Other guesses? Let's take a vote. How many people think that when I blow between these two, they will go apart from each other?
Considering the diagram says apart.
How many people say they're going to come together? Okay, so let's find out. Here we go. Just going to hold them like this. So yeah, they fly together. And the reason that they fly together actually has to do with something known as a pressure system. Whenever you have fast-moving air, you have a low pressure in that area. If you ever watch the weather, you know that a lot of times when they talk about low pressure systems coming in, those come with big storms and high winds because that low pressure pulls in that air. High pressure are areas where you don't really have much air movement. So the reason that the paper comes together is because you've got low pressure here. If there's higher pressure on the outside, it's going to push those two pieces of paper together. And this concept has a lot of different applications. This is actually the reason that airplanes fly. So wings are not just designed, like angled so the plane goes forward and climbs like that. They're designed very specifically so that the top is more bowed than the bottom. The bottom is really flat. And they're designed that way so that the air going across the top moves faster. And again, faster air means a lower pressure. And then what that means is the higher pressure underneath will give the wing lift. And that's the main way that these airplanes and airplane wings work. That's what gives you that extra lift to get the elevation that you need. The fast-moving air is going to draw the wing upward. And there's just another diagram there. So the faster moving air you have, that's the direction that everything is going to be pushed. In this case, faster air is up top. And this has a lot to do with baseball and tennis ball as well. So if you have a baseball and you throw it normally with no spin whatsoever, I suppose that's not normal then. If you knuckleball it, then the air moves the same around both the top and the bottom. But if you can do baseball or tennis ball, if you give these two things backspin, I really wish I had my old projector back so I could do this better. I don't think it's going to work here. But if the ball is headed to the right and you give it backspin, that ball is actually going to lift up a little bit. And the reason for that is because as it's going this way, it's taking the air in front of it and it's pulling it over the top. And as it does that, that air is moving faster than the air below it. And because that fast-moving air is a low pressure, then the higher pressure from the bottom pushes it upwards and gives you that extra elevation. And that's what's happening with those. Now, if you do the same thing, whether baseball or tennis, and you give the ball topspin, you know exactly what's going to happen. It's going to dive down. The reason for that is because now this ball is, still traveling to the right. So if it has topspin, it's taking the air in front of it, bending it underneath. So now this is the low pressure down here, and this is the high pressure here, and that's what pushes the ball into that curvy motion going down because of the pressure difference. Questions on this?
No, that makes sense.
Cool. Who likes party balloons? Yeah, me too. Whose favorite color is purple?
Me.
Couple people, very good. Yellow. Nobody for yellow. Poor yellow. Red. Ooh, a lot of people for red. Teal. Nobody for teal. This was the winner last hour. White. Nobody. I don't know what that one is, if this one's purple. Magenta, maybe? Orange. Green. Regular blue. Okay, cool. So, speaking of these party balloons, they are all inflated with a certain amount of pressure. And strange things happen with pressure and volume if you change the environment you're in. For instance, who here likes sun chips?
Oh, God.
Sun chips are awesome. I especially like the Harvest Cheddar kind. Except, number one, it's hard to put them down, and number two, if you go too fast, they kind of scratch the roof of your mouth.
Hot take, original's the best.
Oh, really? I'll have to give those a try. So let's say you've got your sun chips, and you're going on a road trip to Colorado, and there they are. They look beautiful. Now, you get all the way to Colorado without eating them somehow. Any guesses on what's going to change about this bag and the chips? If you start in Milwaukee, which is roughly sea level, and then you go all the way to Colorado with your sun chips, how's this bag going to look different?
The bag's going to be full of air.
Yeah, the bag is going to expand.
That happened to me.
Oh, really?
Yeah, I went to like a park in California, like a national park, and the bag got really big.
Okay, yeah, it must have been very high elevation. And the reason that this happens is because of a special equation, which is on your formula sheet, PV equals nRT. These two letters you can kind of forget about. They're a constant. P is pressure, V is volume, and T is temperature. Now, in your car, you're probably going to keep the temperature the same. So the whole right side of this equation is going to be the same value. But if you go from Milwaukee all the way to Colorado, Colorado is a much higher elevation, which has less pressure. So if the pressure goes down, the volume's going to go up. And that's why your sun chips have ballooned the way they have. And that's how that works. Hot air balloons are kind of the same thing. If you're in that hot air balloon and it starts to descend, they release the hot air and you can see fire usually coming straight up into the balloon. So when you raise the temperature then, what you're doing is you are decreasing the pressure. And when you decrease the pressure of something, that causes that object or that air to rise up. This is why hot air rises. It is less dense. It has less pressure. And so that's why you release heat into a hot air balloon to make you go up. Makes the air less dense, gives you more lift. Speaking of heat, if we're talking about thermodynamics, we got to mention this. Heat is the way in which energy is transferred between a system and its environment due to a temperature difference between them. It's also the amount of energy that is transferred. So in thermodynamics, we talk of heat as being the thing that goes from one place to another. And I'll mention this again later. But if you are, wintertime and you're in your nice cozy house and you open the door to the outside because you just want to be a jerk, if you do that, thermodynamically, you would talk of it as the heat leaving the house. You would not talk about it as the cold coming in. We always speak of things in terms of the heat. So these are some fancy, not too fancy actually, equations that you can use to figure all sorts of things out in terms of vaporization and fusion. You can use these to calculate exactly, how long it would take a certain ice cube to melt under certain temperature conditions or pressure conditions. You could figure out how long it would take to freeze something that's in an ice cube tray. Very basic calculations that we don't need to spend too much time on, but they're up there and they're on your formula sheet. And this graph just shows you how really interesting all the different elements, especially water, are. Because you can have ice down here, and then of course there's a space where you can have water and ice, very specific temperature. And then you can just have water from 0 to 100 degrees Celsius, water and steam at 100 degrees, and if you go above that, the water will turn into steam. So it's pretty amazing that one molecule can actually change through all these phases. It's pretty amazing. So yeah, that's the sort of thing we would talk about more if we spent more time dealing with this. Of course, if you really wanted to get into it, we could say, how long will it take ice, if you put it at 200 degrees, or maybe 400 degrees, pizza cooking temperature, how long would it take to turn to steam? Those are the fancy calculations we could figure out. So first law of thermodynamics is that the energy before must either be equal to or greater than the energy you end up with after something is done, after some sort of work is performed by a system or a machine. So in other words, your change in energy is equal to heat, Q, if you remember that from the energy section, minus work, W. So your change in energy is just the amount of heat that's produced by the object minus the amount of work that the object or machine actually does. And that's all the first law of thermodynamics is. We could visualize it here, and I'll go ahead and read the science-y thing. This is NASA speak. Any thermodynamic system in an equilibrium state possesses a state variable called the internal energy. Between any two equilibrium states, the change in internal energy is equal to the difference of the heat transfer into the system and work done by the system. I should have you memorize that, I think. So basically what we're saying here is, you can see we've got these weights on top of this mechanism, and it's, it's at a certain pressure here, and that's pressurizing this gas below it. If you add a weight to that, and it becomes more pressurized, then your overall energy difference is going to be equal to the amount of work done, the distance, minus the amount of heat that's put out. Because when you pressurize gas like that, the temperature is going to go up. So you would just take the difference between those two values, and that's what your overall energy would be. That's what the first law of thermodynamics says. Second law of thermodynamics is the one we're going to spend most of class time on, and you can say it in a lot of different ways. This is one way. It is impossible to make a heat engine that puts out the same amount of energy it takes to run it. In other words, you can never make something that is perfectly efficient. If it takes, 100 joules of energy for the system to run, it's never going to put out exactly 100 joules of work, because you're going to lose some of that energy through friction and heat and sound and other things. So you can never make anything perfectly efficient. That's one of the ways that you can talk about the second law of thermodynamics. The more fun way is going to come later. But speaking of engines, I mentioned that we talk of energy as flowing, we talk of heat as either coming or leaving. It goes from heat to cold. So our energy then is going from something of high temperature to something of low temperature. That's the natural way that this energy is going to flow. So one thing you can do is take advantage of that heat flow if you've got a temperature difference between the two, and you can kind of siphon off some of that heat in order to do work. And that's, what an engine can do. You take that temperature difference and use it to perform some sort of work on something. So again, heat and energy does not flow spontaneously from a cold object to a hot one. It goes from hot to cold. So, if you need to cool something down, instead of using that temperature difference to do work, you have to do work on that system to make the energy flow from cold to hot. In other words, you want to keep this nice and cold through a refrigerator or a freezer or something like that, or an air conditioner. You have to have something performing that work in order to, keep the system cool instead of making it hot. Flows in the opposite direction. And here's another example. You have to do work on something to turn cold air into hot air. And of course, this is usually done with your furnace in the basement, which is probably run through a natural gas system. It takes in the air from the outside, heats it up by burning that natural gas, and it comes in as nice, cozy, warm air on the inside of your house. Okay, trains are cool. This is a steam train, and you see these in a lot of old westerns. And I'm going to show you exactly how these work, although it is kind of a simplistic thing. There is more that goes into these than what I'm going to show you, but it'll give you a general idea of what's going on when you do see these things at work. So this is a little animation. Usually what you see in movies with these trains is you see people shoveling coal into a big furnace that gets super hot. So that's step one. You need very, very hot temperatures. Now what you don't usually see is that there's a conductor also in the furnace. So that conductor is going to take that heat and it runs through something that might be like water here, and that water produces all sorts of steam. And that's why they call it a steam engine, because that's where all the energy to produce the motion comes from. So that steam evaporates, and because it's hot, it needs to expand, because its gas form is going to take up more volume than its liquid form. So it expands up, goes through this passageway, and it kicks open this door here. You'll see it kick open in the next step. Kicks it open, so that causes this bar to go from the bottom right here, and then when it kicks it open, pushes it this way, and then it comes back around. So as a train is traveling, the only part that's actually being pushed is when this bar is, even and on the bottom. And that's what's causing it to move forward. When it comes back up like this, it just comes back up due to the momentum that it received from that original push. So then as it comes back forward, it's going to take that steam and it is going to then push it up, and then it's going to come out the exhaust right there and into the air. And that's basically what's happening in a steam engine. Obviously, it goes a little deeper than that if you wanted to get into it, but that's basically what you're doing. You've got a conductor that's producing steam. That steam is forced down a passageway. That causes the wheels to turn. There's lots of intricate mechanisms so that this releases at precisely the right times so that you can speed up and slow down the train. But that's the main idea. Now, the neatest thing about the second law of thermodynamics that we want to talk about has to do with something called entropy. Anybody ever heard of entropy before? No, okay. Maybe one. So entropy is basically another way to say the word disorder. And the second law of thermodynamics says the total entropy, or disorder, of an isolated system that undergoes a change cannot decrease. In other words, you can't go from something that is disorderly to something that is orderly all by itself. It has to have some sort of intelligent agent doing work on it for that to happen. For instance, let's say you've got a nice organized ice cube here, and then it melts and becomes disorganized. We would say that the entropy of this system has now increased. Its disorder has increased, and we abbreviate entropy with S for some reason, probably because E is used everywhere else. We use E for energy, among other things. But yeah, so the entropy and disorder has gone up. Now, you're not going to be able to turn this puddle back into an ice cube, even if you freeze it again. It's not going to spontaneously do that. You need to perform a work on that water in order to get it back into that cube shape. You have to put it back in the ice cube tray and throw it back in the freezer. That's never going to happen on its own. Its disorder will always go up. It will never go back down unless you perform work on it. And that's what the second law of thermodynamics says. Questions on that concept? Cool. Here's the sciencey way of talking about it. There exists a useful thermodynamic variable called entropy, a natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. See, it says irreversible process. What that means is, like, if you're in a bathtub and it's nice and warm, and then you turn on the cold water, what's going to happen is the entire tub is going to get a little bit colder. You're not going to have the right side of the tub be, hot and the left side of the tub be cold. They're intertwined. It's all going to mix together. You cannot separate the two. That would be irreversible. So yeah, that's what that means. And one of my favorite ways to talk about the second law of thermodynamics, and one of the big discussions that have been had by both sides of the debate here, is the second law of thermodynamics versus evolution. And I mean that in two ways. Cosmological evolution, the idea that the Big Bang created everything and that it all spontaneously organized, and chemical evolution, the idea that organized cells somehow got that way on their own without any work, without an intelligent designer to cause that to happen. So there's all sorts of discussion here, and I'm just going to give you the gist of it before we get into it in earnest over the next couple days. But just think of it like this, in terms of entropy and disorder. Supposedly from the Big Bang and no creator, no God, from this gigantic chaotic explosion, what we got was an organized solar system within an organized galaxy in a very organized universe. And within our organized Earth, we got life spontaneously organizing together. And it's just, you need all this organization when in reality there's no way we see organization apart from a creator or apart from an intelligence that's making it that way. So you can kind of see where the basis of this discussion is going to start. So let's just talk briefly about the Big Bang and what would happen. From a gigantic explosion, supposedly we get all this organization. And I don't know about you, but every time I see Wile E. Coyote try and explode something, I see all sorts of disorganization. And that's exactly what would happen if there was a gigantic explosion. Yeah, you could have gas and dust and everywhere, but it's not going to spontaneously organize itself. Like, just imagine if I started passing out cigarettes to you guys right now, and we all started smoking. If we all started smoking, this room would get all smoky, right? You would not find all the smoke gathering in one part of the room and organizing itself into a sphere, or organizing itself into a pyramid over in another area. So you do not spontaneously get organization from disorganization. Yes, Andrew?
One thing that I don't get is, how would an explosion make, almost a perfect line of just, spheres all made out of different things?
Well, the answer to that is it can't.
And then, don't know. There's just so much.
Because here's the thing.
There's so much missing.
Yeah. Whenever you see a yes, sure. Whenever you see an astrophysics textbook talk about star formation or planet formation, there are barriers at every level of that. Even if you could somehow, because, I mean, gas is gas. It expands. It does not come together to swirl around itself. It's just not how gas works in the real world. So a lot of times they say you got these swirling gas clouds of, dust, and over time they swirl together to create, planets and solar systems.
That's a lot of dust.
But the first thing that needs to happen is you need to somehow create something that's solid. And in order to create something that's solid, that gas has to condense to a point where you have something solid. And even if, so that's the first part that nobody knows how it could have happened. But if you finally get something that's like 3 feet long, and you've got all these different things that are 3 feet long, what do you suppose happens when they're swirling around and they hit each other? They disintegrate. They break up because they're not strong enough to gravitationally attract each other yet. So that's another bit of kind of magic wand waving that the scientific community does in the astrophysics world.
Well, how does dust make humans?
It doesn't. And that's where I'm going next. So yeah. And you get that even once you get to the point where you have these little planetesimals that are miles across. They're still not strong enough to mutually attract each other. They'd break up if they hit each other. So every step of this, you run into all sorts of difficulties, and usually in astrophysics textbooks they say, we're not quite sure how this happens yet, but here's, what must happen for this to occur, because they're assuming that there's no God.
So if they don't know, then why do they hate so much on people who, think that they know other stuff?
That's because they look down on the Bible, and they look down on a creator. They feel like they're so arrogant that they feel like
if there was a higher power, they wouldn't be happy with it.
Yeah.
They want to be the higher power.
Yeah, they think that we're smart enough that we've figured everything out as though it could have happened without a creator, when there's no way it possibly could have. And that's a huge, huge thing. And that's not just for planet formation. It's not just for star formation either. You run into the same problems with star formation. But when you look at, how about this? When you took biology, is a simple cell simple?
No.
No. It's super complicated. And
Mitochondria.
right. It's the powerhouse of the cell, right? So, if you somehow have, if somehow the inevitable, if the impossible happens, and you do have something like Earth, the question is whether or not a simple cell could actually form. And the answer to that is no, because simple cells are not simple. You've got all sorts of different complex mechanisms at work in even the simplest living cell. And by the way, if somehow that happened to exist, in order for cells to actually work and remain, they have to be able to replicate. If they can't replicate, then once all this magic happens, it's all for nothing. So you're never going to get a cell from non-life in the same way that you're never going to get a planet from swirling balls of gas and dust. It's way too complicated. And it goes even deeper than that because there's information within these cells that tells every bit of this how to function. Where did that information come from? It's not enough just to have all this. It has to be programmed. So just to kind of give you a visualization of what I'm talking about here, this is a mousetrap. Now let's say you set this up, but you don't put any cheese or mouse food there. Is it going to work?
No.
No.
I mean, maybe by chance.
Yeah, if you've got a really stupid mouse. Yep. What if you set it up and you get rid of this spring here?
No.
No. What if you set it up and you get rid of the bar?
No.
No. What about if you get rid of the wood?
No.
No, of course not. You need everything for it to function the way it needs to function. And if you get rid of any little bit of it, it's not going to work at all. And the cell is the exact same way. You cannot have just one part of it existing. It all has to exist at the same time. It is irreducibly complex. That's the term for this. Everything has to be present right away at the very first time for this to work. Yes?
What if God just started creation with the Big Bang?
Well,
Right.
that's one of those things where we can look at the evidence and see if it looks like the universe really was made by a Big Bang, by an explosion over millions of years.
So God just did it.
He did it, and he tells us in the Bible how he did it. That's ultimately why we know it wasn't through a Big Bang.
Yeah, no, I'm saying just to start it off.
Right.
It's wow. And then he was like, alright, this.
Sure. Well, there could have been some explosions during Creation Week, I'm not sure. But we know for sure, first by the Bible, and second by observations on our Earth and in space, that everything is much younger than the billions of years that the scientific community says it is. Everything points to the time scale of the Bible. That's one of the things we talk about in comparative origins. That the world and everything in it and everything outside of it is just 6,000 years old or so. And when you actually look at the real evidence, not anecdotal evidence that's taken through bias, it all points exactly that way. So yeah, when we're dealing with these cells and everything else with it, everything would have had to exist functioning, ready to go right away. It cannot develop piecemeal, cannot develop one bit at a time. It's irreducibly complex. And a lot of biologists, and especially those people who are involved in genetic and DNA research, they realize this too. There's a guy named Francis Crick who got the Nobel Prize for his research in genetics and DNA a while ago. And he was an evolutionist. He believed in the Big Bang and evolution and all that life spontaneously arose until he started doing that actual research. And he realized that it's too complicated. It's too impossible. There's no way you could get the genetic code to have even a simple cell just spontaneously arise. And so he changed his belief system. He did not go to the Bible or the true creator, unfortunately, but because the scientific community is so biased against the Christian faith that any answer apart from God, even if you have to invoke a creator, is okay, as long as it's not the God of the Bible. And so what Francis Crick did is he believed that life is too complicated to form on its own, so what he believed was that aliens came to Earth and seeded life on Earth. It's called panspermia. And that's what his worldview then was based on, which solves nothing, because it just pushes the problem further back. Because if aliens seeded life on Earth, then who created the aliens? And if someone seeded their lives, then who created the aliens who created the aliens? And you can only push this problem so far back because this Big Bang supposedly happened in the finite past. Yes?
Do you think aliens exist?
No. I mean, I believe that experiences people have are real. I know people get abducted and things like that, but I don't believe it's aliens that are at work. I think it's a demonic thing that's going on. And we can talk about more about that at another time. We've got some time at the end of the year where I have nothing planned, where we can actually talk about stuff like that. Yeah, absolutely. So anyway, when we look out in space, or when we look in the tiniest cell, everything declares the glory of God. Whether you're looking into the deepest, tiniest little virus, or whether you back out and you look at the universe on its grand scale, you see the beauty and the design that could only come by the hand of an almighty, benevolent creator. That's exactly what we see, and whenever we look out in space or deeper into something, whether it be a cell or anything else, we become more and more confident of that answer, that we have been created by an organized, wonderful creator. And that's what our God is. Everything in the world and outside of it points directly to him, not away. The last thing I just want to show you guys here, if we actually used a textbook in this class, you'd see these numbers. And these are the universe's constants. They're physical constants. The one that we talked about when we were dealing with orbit is this guy here, Newtonian constant of gravitation. And it is very fine-tuned along with all the other numbers on this list. Every single number on this list is fine-tuned to a degree that if it was changed in the slightest, not only could you and I not exist, but the universe could not exist either. If you change any one of these numbers in that Newtonian gravitational constant, say you make it just the slightest bit higher, then gravity is too strong. now not only can planets not form, but you and me would not be able to exist. Everything would collapse in on itself, and you'd have a bunch of black holes all over the place. We would not be able to see, we would not be able to do anything, and neither would our universe. There would be no stars, there would be no light, because everything would collapse in on itself. Gravity would be too strong. If you make this number the tiniest bit lower, then you don't have enough gravity for molecules to actually stay together. And they would depart, and they would go off into space. So every molecule in your body and in my body, and anything else that's solid, would detach and start flying off, because gravity would not be strong enough for those objects to stick together. And it's like that for all of these constants. It's like we live in a universe where all of these gears are just exactly right, not just for the universe to exist, but for you and I to exist. And so it's like if someone believes that the Big Bang happened without any type of creator or intelligence, and we're just the result of that random, massive, chaotic explosion, how the heck do you explain how all these constants got so perfect for our universe? And of course, the answer that the scientific community usually comes up with is, well, we're here, and we're in this universe, so even though our universe is perfect, there must be other universes that are not quite as lucky. And we just happen to be in the one where life is sustainable. And I'm not just talking about one or two other universes. They say there are an infinite number of universes out there, because they can't believe how special this universe is. And to think our universe is special, well, that points us a little bit too strongly to a creator, to the God of the Bible. So they're not going to go there, which is super sad. They're blinding themselves to the truth.
And people, they just like are biased to insignificance. They just think that we mean nothing.
Exactly. And you get that way by being arrogant. And that's exactly what the scientific community is. And the vanity of that community is ultimately what is blinding them to the degree they are. And it's really unfortunate. And it's why you get crazy explanations, like there being a zillion universes out there, and us being in just the perfect one. And you ask them how they know that, and they'll say, well, we're here, aren't we? Do you detect the circular reasoning? And the newest way to answer this question is, well, we live in such a perfect universe. It's exactly the way it needs to be. So you know what? Maybe it was created. But again, they're not going to go to the creator. They're not going to go to the God of the Bible. They're going to say, well, we're probably just a simulation running on a computer program created by some alien. So that's simulation theory. I think it's what Elon Musk believes, who is a very intelligent person, who has a lot of good ideas, but that one's not a good one.
Neil deGrasse Tyson makes me mad.
Yeah, me too. So all simulation theory is it's a way to try and avoid the idea of there actually being a real creator of the universe, like the God of the Bible. And it's a way to run away from that. So it's really sad the way that that's done. And even if we were created by an alien, who created the alien who created the computer that created us? And then you got to follow that all the way back through the wormhole to the beginning of the universe. And that doesn't work either because, again, you only have so much time to work with here. You can't keep pushing these things back and back and back. But again, like I said, the heavens do declare the glory of God, and the skies do proclaim the work of his hands, not just out in space, but also the deeper we look in biology and chemistry and genetics and DNA and the genetic code. The more we look in science, the more we see how complicated it is, how amazing it is, and how well it works. And there's no way that could happen without an intelligent designer, without our God, who not only created it, but also sustains it to this very day. And that's something we're going to be looking at more deeply as next week progresses, actually. So,
How can people that are so smart believe something so